This is Psych 222. It is January 25, and today is our first day into the book. This week we want to cover chapters 1 and 2, and then we move on. So we've got a lot of work to do. Let's start in with chapter 1. Chapter 1 is a basic overview of where statistics are used and a little bit about the scientific method. I just want to explain a little bit of my approach using the book this way. A good way to study is as you're reading through your book, you're looking at the lectures here and you're focusing on what I focus on. So we're definitely not going to be underlining every part of the book or anything like that, but I will be focusing on definitions, using examples, kind of starring areas that are really, really important. In other areas of the book, I'm going to skip over and tell you it's not important or really, really gloss over. So you're focusing on what I cover in lectures, you're focusing on assignments, and you're hitting those really, really important areas. The rest of the book is kind of, filling gaps and other topics, okay? So we'll talk about that as we go. First thing to recognize here is statistics are used in the context of the scientific method. Okay, so when you think about science in general, well, science is trying to accumulate knowledge, right? We're trying to learn about nature. Well, as we're going to see, statistics aids us in doing that. Okay, so they're not separate things. Anybody engaged in scientific practice today, virtually everybody engaged, has to understand statistics. You really can't get away from it. Okay, so it's really, really important. We'll see how that works. Here's a useful definition right at the start. The authors say that statistics is the science of designing studies or experiments, collecting data, and analyzing, modeling data for the purpose of decision-making and scientific discovery when the available information is both limited and variable. So oftentimes statistics is phrased as learning from data. Okay? And we will need to define a little bit further what we mean by data. But for now, data is simply information, right? It's raw information. There's a tradition in the accumulation of knowledge called empiricism, okay? Empiricism. The idea of empiricism means learning from experience. Okay, that's the tradition in which science operates, is learning from experience. So when we say learning from data, you can also more generally think of that as simply learning from experience. Now, to make it scientific, we're going to talk about the conditions required for learning from data in a very rigorous way. But it's a very general theme when we talk about learning from data. You learn from data all the time, right? You learn what study strategies work best. You learn how to drive better. You learn to wear a bigger jacket when it's cold outside. So imagine you wear a jacket that does not protect you from the cold. Well, you go outside and you're cold. Next time you go outside, you're going to wear a bigger jacket. You've just learned from experience. Okay? In that way, you've learned from data. And the data, in that case, is temperature, the size and thickness of coat that you're wearing, and other things. So in that way, we all learn from data. But to learn from it in a very, very systematic way, that's what we need to develop as we proceed in the book. Okay. Well, almost everybody, including social scientists, medical researchers, superintendents, public schools, corporate executives, almost everybody deals with data and has to learn from it. Another example of learning from data is the polls, okay? The election polls, that's an example of learning from data, right? Who is going to win the election? Well, they took some polls, and by taking a poll, you're attempting to learn from that information, okay? Now, they talk about some other things here, like the 4-step process to learning from data. We'll talk about that more as we go. Not vital that you memorize those things. And I do not encourage you to memorize things throughout the book. I encourage you to understand, try to understand it, try to get the concept. Okay, behind every definition, there's a concept, and really, really try to get that concept. Well, here's a schematic of the scientific method. So oftentimes in the scientific method, we do things like formulate research goals, right? We all have hypotheses, and these are sometimes referred to generally as models. Perhaps you think that a given vaccine will prevent COVID, right? Will prevent COVID-19. Will the vaccine work? Well, that's an example of a research goal, right? You want to develop a vaccine that will guard against COVID-19. Your research hypothesis in general could be that the vaccine is going to work. That's an example. Well, to do that, to evaluate whether the vaccine works, you need to do something like design a study. And that's exactly what they did with the vaccine for COVID-19, is they designed a study. They had to recruit a certain number of participants. They had to define their variables. They had to get experimental units and a whole bunch of other things to get an effective study. Now, how did that work for the vaccine example? Well, for the vaccine, you had a whole bunch of participants, P. So those are participants. You had participants, and then they randomly assigned the participants to a control group or a treatment group. So that's control and that's a treatment group. And half of the people received the vaccine. The other half received like a sugar pill or some kind of a placebo, something that was not expected to work. So that's what we mean generally when we talk about designing a study, right? What's the problem with simply giving the vaccine to some people and kind of observing them and seeing what happens? That's not a controlled study. So, Pfizer, right? Pfizer, the people who developed that first vaccine, they can't just take the vaccine, start giving it to people and kind of asking them later on, how you doing, and trying to measure whether they've developed COVID. They have to do this idea of an experiment. They have to have a rigorous controlled experiment where you do have that random assignment to groups, so that after people receive the treatment, which is the vaccine in this case, you can compare to a control group. And why this type of setup is necessary is because if you don't do something like this, you don't know whether the treatment is working or not. You don't know whether the vaccine is working. Okay, so let's say for a given person, they get the treatment. Okay, this person gets the treatment and they do not develop COVID-19. Well, you can't conclude based on that alone that the vaccine's working, because maybe the person wouldn't have gotten COVID-19. That's what the control group is for. You don't know if the vaccine is working unless you have this type of setup. So you want to design a good study whenever you do statistics, whenever you do science. It's got to be a solid, rigorous study. Well, there's different steps here. You formulate new research goals, you get new models. So you collect data over here. Sorry, that's the last point. We're going to go this way. You collect data management. So what do we collect on our COVID-19 participants? Right? We collected data. We gave some people the vaccine, some people the sugar pill, and then we observe results and draw inferences. And from there, we make decisions. Now, this idea of inferences here is actually really, really important. And we're going to talk about this idea of inferring from samples to populations. And doing that is going to help us address how our hypotheses turned out and how our model turns out. So here's that last point, is we then formulate new research goals. So after you've looked at your particular study, you've written up some conclusions, well, then you make up new research goals. So you can see there's a little bit of a feedback loop to research, in that you have hypotheses, you collect data, you do experiments, you get the results, and then that informs the hypotheses again. It always goes round and round like that. I will give you an example from that Pfizer vaccine. Well, in the treatment group, 8 people got COVID-19. Right? There were still 8 people who got COVID-19. Out of about 18,000, there was only about 8 that actually got it. Here, there's about 162 that got it. Well, what would be a new research goal? A new research goal would be, why did these 8 people get COVID-19? Right? What was it about these 8? They got the vaccine, but they still got COVID-19. So what was it about them that may have promoted them still getting COVID-19? They were not protected from the vaccine. And that becomes a really good new research goal, a new research question. And from there, you're going to design a new study. So that's that kind of circular idea of the feedback loop to conducting research. Now, in this book here, you may have noticed that the book is really, really, really big. Okay, this book is really big. It could be used easily for a year-long course and even longer in some cases. And if you take upper division courses or you go into further education in stats and research, you will explore further chapters like these over here. These are pretty advanced chapters over here. What we're focusing on in this course is we're getting through these earlier chapters, which is basically an introduction to statistics. Okay, let's move on here a little bit. Well, there's some of the above concepts about the idea of learning from data. We gave one example of the COVID-19 vaccine. The book talks about some other topics here, like inspection of ground beef in a large beef processing facility. You can read through this, but what the main idea here is, let's say that you're producing a lot of ground beef, and you want to make sure that the ground beef is clean, it's healthy, and it's safe for human consumption. Well, let's just say that you have, 100,000 packages, right? There's 100,000 packages. Well, if you want to inspect the beef to make sure it's safe, right? We know those little tags you see on meat sold in the store that says inspected by the Department of Agriculture. They can't inspect every piece of beef. They can't inspect every piece of meat. What do? Well, they take a sample, right? They take the sample of 250. So if I have 100,000 and I take 250 and I study these, right? I'm going to study these 250. If I study the 250 and I conclude their quality, so there's no defects, well, that's great. If I've randomly selected these from the 100,000, that's even better, right? Because then I'm trying to get a representation of that wider group by studying the smaller group. The idea here is that instead of having to study 100,000 observations, which would take too long, it'd be too expensive, we instead study a smaller subset of that wider group. And we study the 250 in this case, and then if these look okay, then we try to make an inference that the 100,000 are okay as well. Now there's another aspect to this too, that you study 250, what if 249 are good, but then you have the one that's bad? So in this example of the ground beef, one ground beef package wasn't good, or there's a problem with it. What should you do, right? Well, in some cases, maybe that calls for stopping the process, right? Especially if this number gets to be large. If this is only one bad package. What if there were 10 bad packages? What if there were 20, etc.? Well, then at some point, you say, based on the information in the sample, we need to halt production of beef. And then there's even sometimes a recall of beef. And that's what you sometimes hear about in the media, that there's been a recall of certain beef products or other products. Um, Same idea with dog food, right? Sometimes when there's a recall of dog food, you can be sure they cannot inspect everything. You inspect a smaller sample, and then you try to draw a conclusion of that wider group. And statistics, as we'll see, are very, very important in that regard. The idea here to emphasize too is that if there's only maybe one bad product, maybe you don't halt the process, you just continue on. But as this number of bad cases increases, you start thinking maybe you should stop the process. They have to do that with cars as well. Whenever there's a problem with a car, if they sell 100,000 cars, right, you can apply these examples to almost everything. If they sell 100,000 cars, but there's only one bad car, there's only one problem, well, you don't hear about the recall usually. But if this starts to grow in size, then maybe they have to recall the car and halt production or change the way they produce things. So that's an example of where statistics can be used, and we'll see how that works. Other areas where statistics are used, here's an example. Is there a relationship between quitting smoking and gaining weight? So do people who quit smoking tend to put on weight? And we could assess these types of relationships using such things as correlation coefficients and other things. So there's another example where stats are used. You can read through the other couple examples. Well, here's one we talked about, the idea of public opinion towards a question, issue, product, or candidate. Those are those polling examples that you hear about in the newspapers. So that's a really, really obvious place where they're trying to find out who's going to win the election, for instance. But what's the nature of a poll? The nature of a poll is to study a sample, right? You're studying a smaller set of observations and you're trying to draw an inference. Remember that inductive idea, inference? You're trying to draw an inference to the population, right? So if they study, 5,000 people and they find out that, 55% say they're going to vote Biden and 45 Trump, well, then they try to make an inference of how the election will turn out. And that's one example where we've seen, especially in the 2016 election, that didn't work out that well, right? When they tried to make predictions of the election, they ended up being way, way off because they still had to rely on how people answer, right? So whenever you ask a question of somebody, like who you will vote for, your data are only as good as what the quality of that answer. So if some people in 2016 said they would vote Clinton, remember it was Clinton versus Trump, if they said they would vote Clinton when in reality they were voting Trump, well, then they're lying. And it's really hard to get around those types of problems with those subjective reports. Okay, so we're going to see how stats are used to help address this sample to population problem. Well, here it is. Here's a schematic of it. Sets of all measurements in the population, right? That's that wider group right here. And that could be almost anything you wish to study. As we said, it could be Americans for voting behavior. It could be those packages of meat that are being produced by the facility, right? What else could it be? It's endless. It could be people suffering from COVID-19. The whole bunch of populations. And this is what science seeks to know about populations of observations. That's the primary goal. But we can't collect populations usually because why? What do we know about populations? They are usually very, very big. They're very big in size. So we're restricted to studying samples. You get the set of measurements from the population, and that is your sample. The whole process of statistical inference works like this. Study the sample really good. Maybe compute something on the sample like a sample mean. Okay, there's an average. There's a sample mean with a bar on it. And then take that sample mean and draw an inference towards the population. So statistics will use statements like this. If the sample mean is equal to, say, 100, let's say for whatever we're measuring, if it's equal to 100, what can we say about the population mean? Right? What can we say about the population mean? Because again, I want to stress that this is what we're really interested in. Here is the population. We're only studying the sample to get a glimpse into the population. You know, when they do those studies for the vaccines for the COVID-19, they're really not interested in those 20,000 people they collected for the trial. What are they interested in most? They're interested in how this vaccine is going to work on the world, right? They're only studying those 20,000 for the vaccine to give us an idea of what's going to happen when they give that vaccine to the population. So in that respect, the sample is very interesting. I don't want you to think that the sample is not interesting, but this is the most interesting aspect. And statistics will help us generalize and evaluate how well this can tell us about this. There's our sample. How well will it tell us about the population? Okay, so some definitions here, and here's an example of when you read a definition, you really should not memorize the definition. And you've heard me stress this before, and I'll repeat saying it, because if you memorize this, a population is a set of all measurements of interest to the sample collector. Well, that may not give you the complete concept. And the best way to get the concept is to refer to examples like we're talking about, like the COVID-19, like the beef packages, like the polling example. Really try to conceptualize it. You never just want to just memorize this and walk around with the definition, because this definition arises from the concept. So always try to get that deeper meaning of what's there. A sample is any subset of measurements selected from the population. There again, well, we've seen examples of this. So if you were to memorize this, that doesn't necessarily mean you even understand what it means, right? The important thing is to be able to use the term, to be able to look at it in different contexts. So if we apply it to a new problem, can you identify the sample? Right? Here's an example, coin flips. Okay, imagine I have a coin and I want to know the probability of heads or tails. Well, what's my population? What's my sample? Okay, so you've got your coin and you want to know what is the probability of heads or tails. So in other words, you want to know, is the coin fair? Right? And what's a fair coin? The fair coin is the probability of heads equals 0.5. So it's going to be a fair coin. Half the time it's going to come up heads, half the time it's going to come up tails. What would be our population? Well, if you read the definition, population is a set of all measurements of interest. What's the set of all measurements here? Well, the set of all measurements is the total number of coin flips, right? It's the total number of coin flips. In most cases, that's how we would define that population. We could, if we wanted to, define it as being 100 coin flips or 1,000 coin flips. But really, when you think about it, we would like to know how all those coin flips behave. So we could say that our population here is infinite in size. It's infinite in size because you can keep flipping that coin forever. There's an example that if you understand the concept, you really start to appreciate what these words mean. A sample is any subset of measurements selected from the population. Well, again, with the coin. what would be considered a sample? Maybe 100 flips, right? You're going to flip it 100 times, there's your sample. Notice as well that when we say it's a subset of measurements, here's another example that if you try to memorize that definition, well, we're not really taking measurements of the coin, right? You're not really measuring anything, you're just flipping it. In other cases, we will be measuring things like weight, like height, but when you're flipping the coin, it's not in the same way a measurement. So that's why you have to be careful when you look at the definitions. You try to generalize it to the wider concept, okay? So we've talked already about why study statistics. Statistics are used everywhere, okay? So they're used everywhere. They're used, we talked about it in political polls, published research of scientific research. They're used in science all over the place. So if you wish to go into a scientific field, if you wish to go into a clinical field, any kind of field is going to be using statistics. That's why it's so important to know, so important to understand. Two things that are incompatible is wanting to be a scientist and not wanting to study statistics. That's not going to work. You've got to be able to study stats and you have to be able to understand them as well. Even things like blood test results, right? When you get a blood test, and you get your cholesterol measurements. Your cholesterol measurements will sometimes be high and low. You're low or you're high or something like that. And then if you score within this range, let's say maybe you're okay, the doctor says you're fine, you're within the range of acceptable cholesterol levels, right? But if you're beyond that, then that sometimes becomes concerning. Well, it's interesting to learn, why is this a concerning observation, yet not if you're in here, not if you're within the range. And statistics help us identify those extreme scores. And also if we have a score here, well, this score is not much different from this score. So should we really consider this one to be really extreme and this one not? And statistics are going to help us answer questions like that. Okay, so they're used everywhere. Statistics, it's not about causes. Okay, it's not about causes. When we talk about stats, we're not talking about causes. Talk about causation. Causation is really a different thing altogether. You need a really, really good research design in order to even think about talking about causation in most cases. Sometimes you can talk about causation even without an experiment, but it becomes very challenging. So it's just to know that as we go on through the course, we're not talking about A causes B. We're often talking about things like A predicts B. And those two things are different, right? So if I tell you that the temperature outside can help us predict what season we're in, right? Temp predicts season. Well, even if there's a highly predictive relationship there, that would never say that, we'd never say that temp causes the season, right? We would say that temp predicts what season we're in, but causation is a whole different thing altogether. And like I say, making causal statements is really, really hard in science. And we'll talk about issues of causation as we go on, but just know that we're not primarily going to be able to answer that using stats. We will talk about this as we go. What are statistically significant findings? That discussion won't make very much sense now because we haven't studied what statistical significance is. Some other things here that you can read through. More applications of statistics, defining the problem, obtaining information from massive data sets. These days, there's a big movement in statistics, computer science, areas like that, that deal with big data. Okay, and the idea of big data is because of computing technology, a lot of observations can be collected. For instance, if you're on Amazon or something like that, well, Amazon can collect a whole bunch of data about what you're purchasing, when are you purchasing it, and they can use that data to help target ads, to help predict what you're going to buy next, right? Have you ever noticed that in Amazon when you buy a new computer, the next day you see an advertisement for a keyboard, right? It just pops up in the window in your Amazon screen. Well, that's all by design because they know that people who buy computers often want to buy a keyboard next, or they often want to buy a monitor next, and things like that. And they're making those predictions based on pretty large data sets most of the time, because the data is very, very easy to collect because they can just kind of monitor your purchasing behavior. In business, statistics are used a lot in estimating future sales. Well, that's kind of like what we just talked about with the Amazon example, predicting demand on a power grid, estimating server downtime, whole bunch of things where stats are used. Assessing risk. Statistics are used for rates for insurance premiums. We can talk about that example for a long time, and we will throughout the course, but have you ever noticed that when you purchase insurance, they kind of classify you into different groups of risk, right? So, if you buy one of those, you ever wonder why when you buy one of those motorcycles, I'm going to try to draw a motorcycle here. There it is. And there's the muffler. Okay. Some of those motorcycles that you buy, the ones that have a lot of cc's, they have a lot of power, a lot of displacement, the crotch rockets, right? Well, those bikes are kind of made for racing, and you're going to pay a higher insurance premium if you buy one of those bikes than if you buy a different motorcycle, or you buy a car that doesn't have as much horsepower. And one of the reasons why you do pay a higher premium there is because they've looked at data sets that have classified people driving these types of motorcycles as more of a risk of getting into an accident. So statistics and big data sets and data in general are used for estimating those insurance premiums. And many of the people who study those things are called actuaries, and they work in this all day trying to set those rates for insurance companies. And it's very, very interesting. Identifying sequences, determining customer preferences and online purchases. Well, we just talked about that. Grouping, placing customers or events into cluster of related items, and analyzing, predicting relationships between demographic characteristics and purchasing patterns. Right, there's another example. They try to put you in groups, right? Are you the type of client or the type of customer who may be interested in product A or product B, right? And again, to use the computer example, if you buy a computer, well, then maybe you might be interested in a monitor. Sports advertising does that as well, right? So, they'll advertise different things for sports. They'll advertise different network channels, trying to target the consumer. So statistics and data in general are used for those types of things. Of course, we've talked about the ideas of medical procedures and COVID-19. The idea of a medical procedure here, where stats can be used, is assessing risk. So let's say that you have to assess the risk of getting surgery or not getting surgery. Now, suppose the doctor says that you have a minor heart issue. Okay, there's the heart. You have a minor heart issue, but maybe it's not too risky, right? Maybe it's not too big of a problem, but surgery would help. Well, then you have to assess the risk. If I get surgery, are there any risks to the surgery? If I don't get surgery, well, how much risk is there from still having that small heart issue? So that becomes an example of decision-making using statistics. And for that, we're going to need the idea of probability, because we're going to want to assess the probabilistic risk of getting the surgery versus not getting the surgery and just tolerating the slight heart issue. And we're going to see how statistics can be used for those things. Okay, well, we don't need a better example than the COVID-19 pandemic again, new drug product. Okay, we talked about the vaccine. They're also looking for treatments for COVID-19. Well, statistics can be used to determine the effectiveness of it. And again, that goes back to that idea of, taking people and putting them into a treatment or control group and doing those experiments to try to see if the medication or the drug works. And in clinical trials, statistics are used all the time. And we talked about this placebo idea, where you just give these people a sugar pill that doesn't work, and these people, in our example, get the vaccine. Okay. Okay. Other things here where statistics are used. Again, we're just looking at a global overview of where stats are used. It's used in criminal investigations as well. DNA technology has come a long way, where they can identify if they have samples at the scene of a crime. They can get that sample and analyze the DNA sequence of it and potentially match it up with the perpetrator. And that's really, really important, because they can match that DNA to the perpetrator and then evaluate the probability that that would just happen by chance. So we're going to see how statistics can be used and probability can be used to kind of link those two things up. What we're going to see throughout the course as well is there can be a lot of error as well in stats and using statistics to make inferences. Sometimes we make errors, we're not right. You may think that something is the case or that there's a relationship, but sometimes we could be wrong too. But statistics can be used for things like DNA technology and trying to get a match. And also that helps in court cases, right? So, if they try to link the DNA sequence to the perpetrator, well, then they're going to bring in the expert to testify what's the probability of such a link. And so statistics are used in the courtroom a lot with experts testifying on what those probabilities are. Okay, more examples, some other examples here you can read through. I think we've pretty much covered it. Assessing public opinion. We've talked about that in terms of polls, but you can have a whole bunch of other examples in terms of election polls and all kinds of different things. And when you look at this question, what was the population of interest to the pollster? Right. Well, they have to deal with that when they talk about elections. What's the population you're inferring to? What questions were asked and how were the questions phrased? If you are going into psychology, sociology, education, any of those areas, what do we know? We know that people like to give out surveys. You like to collect data from people to find out their opinions on things. Well, when you do that, you have to know how to formulate good questions. And that is a little bit separate from the field of statistics, and that all has to do with measurement. But all of those things are really, really important, right? So when we think about that voting behavior, sometimes it can be hard to find out who will people vote for. So you got to make sure you phrase those questions really well, as one example. Okay. One note to the student here, you can read through this. We think with words and concepts. Okay. A study of the discipline of statistics requires us to memorize new terms and concepts, as does the study of a foreign language. Commit these definitions, theorems, and concepts to memory. Now, again, I just want to stress that the memorization here will only get you so far, because you want to look underneath of what the concept is. So again, I encourage you not to just recite a definition over and over. You want to get the concept. So imagine if you're studying with a study partner and you're talking about what a sample is and what a population is. It would be a huge mistake to just spin off that definition as you memorized it from the book. That's not going to help us. You don't want to do that. What you want to do is explain it in your own words and use examples like we've done in the chapter, or even other examples, and discuss the material. Okay, that's a really, really good thing to do. Discuss it, get the concept, but don't just memorize the definition. You can look at the definition and read it, but seek a deeper understanding. Okay, so I think that's about it for chapter 1. There's a brief summary, and there's some exercises. Some of those exercises from the chapters may appear on assignments as we move forward. We're going to end there for today, but on Wednesday, we are going to start in talking about surveys and experimental studies to gather data. We've talked about experiments a little bit already using our vaccine example, but we're going to distinguish next time between experimental studies and observational studies and surveys and things like that. And we're going to see a little bit more of where statistics can be used in that process. So that's it for today. Nice introductory chapter. Wednesday, we're into chapter 2 and continuing on from there. Okay, so we'll see you next time.